to Binary Builders. Today we are tackling a classical graph algorithm that's both elegant and incredibly useful, the Floyd-Warshall algorithm. Have you wondered how mapping apps find the shortest distance between any two cities in their networks? Or how routers find the best path in the network? That's the all pair shortest path problem. And Floyd-Warshall is one of the best way to solve it. In this video, we will breaking down its purpose, why adjacency matrix is perfect for it, and walk through a step-by-step example. Stick around, it's simple than it sounds. The Floyd-Warshall algorithm is used to find the shortest distance between all pairs of nodes in the weighted graph. It works for direct graph, undirected graph, and graph with negative edge weights. But remember, it does not work with negative cycles. Unlike Dijkstra, which finds shortest path from one source, Floyd-Warshall finds path from every node to every other node in one execution. Floyd-Warshall use an adjacency matrix, not adjacency list, because we need direct access to the distance between every pairs of nodes. Let's say we have a graph with n nodes. We create a n by n matrix called distance matrix. Dist ij equals the weight of edge from I to j. If there is not direct edge, we used infinity. Dist I by I is equal to 0 because distance from a node to itself is 0. This matrix will be updated step by step until it contains the shortest distance between all nodes pairs. The core idea of Floyd-Warshall is simple and powerful. For every pairs of nodes I and j we check, the question is, can the path from I to j be improved by going through an intermediate vertex k? Mathematically, we use these equations to get the shortest path. Shortest path from I to j is calculated by distance to I to j and distance to I to k plus distance to k to j, and get the minimum of these two. We repeat this process for every vertex k and intermediate point. Each iterations allow paths to use the more intermediate vertex. Let's understand this with a small example. Suppose we have 4 nodes A, B, C, D like in this diagram. It shows the weights between 2 nodes. Next, we get the initial distance matrix like this. If there is direct edge, we use infinity. And distance from a node to itself, it is 0. And all other entities shows the direct distance between the nodes. So we can get this matrix. Now, we started updating using intermediate vertex. First, we get A as k. When we get A column and row didn't change. So, we update our new matrix like this. Next, we want the distance to B to B. It is 0. Next, we use the previously mentioned formula to get the distance of B to C like this. B to C distance is infinity and B to A plus A to C is infinity plus 2, means infinity. So the smallest one is also infinity. When we come to D to B, it is previously infinity. But with intermediate vertex A, we can get the formula like this. D to B is infinity and D to A plus A to B is 4 plus 6. It is 10. The smallest one is 10. So we use the 10 to this matrix. After finding this matrix, we use this to create the next matrix which k equals to b. As previously mentioned, using this equation, we can also get the new values. After finding b, we use it to create the matrix k equal to c. After finding c, we use to create matrix k equals to d. If you want the clear idea about this, pause the video and get the calculations. Finally, this matrix now represents all pairs are shortest path. The time complexity of Floyd-Warshall is O of n cube. So, it is best suited for small and medium-sized graph. Common use cases are network routing, distance metric computation, graph analysis in dynamic programming. Floyd-Warshall is a perfect example for dynamic programming on graphs. And that's the Floyd-Warshall algorithm explained step by step. If this video helped you understand all pair shortest path, hit the like button, subscribe to Binary Builders to more deep dives into data structures and algorithms. Thanks for watching. keep building with binary builders.